why giant ships made of metal don't sink? A piece of steel thrown into the water goes straight to the bottom, yet a vessel weighing hundreds of thousands of tons crosses entire oceans without disappearing. This doesn't happen by luck or by engineering magic. There's a very clear reason behind it, and once you understand it, the way you look at a ship at sea completely changes. A piece of steel dropped into the water sinks without debate. That happens because steel is denser than water. Now take that same material, multiply it by thousands of tons, shape it like a ship, and place it in the ocean. Not only does it not sink, it crosses continents carrying containers, cars, grain, and fuel. The contrast is real. The material is the same, but the result is completely different. So the right question isn't, why does steel sink? But rather, what changes when it becomes a ship? The answer starts by breaking down a common idea. A ship doesn't float because it's big, nor because the weight is well distributed. It's also not simply resting on the surface of the water. What happens there is a very specific physical balance. The hull enters the water until it reaches a point where the downward force and the upward force become equal. From that moment on, it stays stable at that level. There's no magic and no hidden trick. A clear rule of physics is acting all the time, and that's what we're going to break down now. When someone tries to explain why a ship doesn't sink, one of these answers usually comes up. It's because it's big, or it's because there's air inside. These explanations sound logical, but they don't address the root of the problem. Being large doesn't make something float. If size alone solved it, a massive steel plate would float, and that's not what happens. And yes, the air inside helps, but it's not the principle that supports the ship. It's the result of a design focused on something more important. The central point is that flotation doesn't depend only on weight. It depends on the relationship between weight and volume. What really matters is how much water the object displaces when it enters the sea. If the displaced water weighs the same as the ship, the buoyant force balances the weight and it stops sinking. If it displaces less, it keeps going down. So the secret isn't size alone or the material by itself. It's the combination of total mass and the space it occupies. That's what completely changes how we see the problem. To fully understand what's happening, we need to talk about a rule discovered more than 2,000 years ago. Archimedes Principle. It states something very direct. Any body submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces. This isn't an opinion or a loose theory. It's a physical law tested, measured, and still applied today in naval engineering. That means when a ship enters the water, it starts pushing water aside. And the deeper it goes, the more water it displaces. There comes a moment when the weight of the displaced water is exactly equal to the total weight of the ship. At that point, the forces balance. The ship's weight pulls downward, the buoyant force pushes upward, and it stops descending. That's when it floats. Not because it's light, but because it has reached equilibrium. This buoyant force doesn't appear out of nowhere. It exists because water pressure increases with depth. The lower part of the hull receives more pressure than the upper part, and that difference creates a net upward force. It's simple but powerful. Now comes the part that really changes everything. What determines whether something sinks or floats is the average density of the whole system, not the isolated material. Steel by itself is denser than water and sinks, but a ship isn't a solid block of steel. It's a hollow structure filled with internal spaces. When you consider the total weight divided by the total volume it occupies, the ship's average density can be lower than that of water, and that's what allows it to float. Think about the difference between a solid steel ball and a massive hull full of compartments. The ball occupies little space for a lot of weight, so it displaces little water before sinking. The ship occupies an enormous volume, so it displaces a much larger amount of water. If that displaced water weighs the same as the ship, buoyancy balances everything. The material is the same, but the outcome changes because the shape completely alters the relationship between mass and volume. That's where engineering comes in. But floating is one thing. Being stable is something completely different. An object can float and still tip over easily. In ships, an essential concept from naval engineering comes into play: stability. Here, three important points appear: the center of gravity, where the total weight is concentrated, the center of buoyancy, where the water's upward force acts, and the metacenter, which is a reference used to measure whether the ship tends to right itself or tip over when it inclines. When a ship tilts to one side because of a wave, the shape of the hull causes the center of buoyancy to shift. That shift creates a righting moment, a force that tries to bring the ship back to its original position. For this to work, the center of gravity must be properly positioned relative to the metacenter. If the center of gravity rises too much, the stabilizing effect decreases. That's why poorly distributed cargo can be dangerous. Stability isn't luck, it's calculated with precision. This makes it clear why a ship doesn't capsize with every wave, but also why it can tip over if something goes wrong. The first risk is water entering where air should be. When internal compartments fill with water, the ship's average density increases. On top of that, this water can move inside, shifting the center of